Okay, so now we will solve this problem. This is the entropy change of ideal gas. Here we have the schematic and the TS diagram. So air is compressed from an initial state to the final state. So this is the air compressor here. The initial temperature and the pressure is given. The final temperature and the pressure is given. The question is asking, determine the entropy change of the air during the compression process. So we need to follow two different ways. Here we need to use the property value from air table, and the second one is the average specific heats. So let's try to solve this problem. Here it is given that it is entropy change of an ideal gas. So you can write down some assumptions and you can say, okay, this is ideal gas. Okay, since you see here actually the temperature is initial temperature is 17 and the final temperature is 57, which is higher than the critical properties of air. You know, the critical temperature of air is negative minus 140 degrees centigrade, and the pressure is 37 atm. So here we have, high temperature if we compare with this critical value of the air, and the low pressure. So we can assume that, okay, this is actually a ideal gas problem. Okay, so this is our assumption that, okay, this is ideal gas problem. So all of our assumption we will use based on the ideal gas. So here, before going to solve the problem, let's try to understand this TS diagram. I already discussed during the lecture the TS diagram. T is actually the temperature, S is entropy, right? So the relations actually between the temperature and the entropy, if the pressure is higher, if I draw it like this, if I draw a dotted line like this here, a dotted line like this, so the entropy will increase this way. So if I say this is the P1, so this is S1 and this is P2, let's say this is S2. So here this is the entropy S1 and this is for S2, that means the final state. What we can see, the entropy is increasing this way. So definitely S1 is greater than S2. So what it means, guys, you look here, when the pressure is lower, entropy is higher. When the pressure is higher, the entropy is lower. We discussed this earlier from the TS diagram. Anyway, so here what we can see, that means from initial state to the final state, the entropy change we can see is decreasing. That means maybe we'll get a negative value. The entropy change, the final answer, it will be negative, because from this TS diagram we can see actually the entropy change, it is actually decreasing. The value is decreasing from initial state to the final state, so we can expect it will be negative. Right, so let's answer the first part of this question. So when we will use the property, the air properties from the air table, so I said we can use the table A17. I will show you later. And we already derived some expression for actually the entropy changes for ideal gas. So you will get two different problem. One is the constant specific heat, another one is variable specific heat. This is actually some exact analysis. So here we need to use what I said is the property values. So when you have the variable specific heats, then we can simplify the equation, and the final equation you will see when you will go through the literature. Then you see this S2 S1, you can say this is delta S. So delta S is the entropy change. It is actually equal S2 naught S1 naught minus the gas constant R ln pressure P2 and P1. Look, you can ask me we have another equation, so why you are using this one? So for another equation, you will see there we have the specific heat Cp, so that we will use when actually we will calculate the second part of this problem. But the first part, it said only the property values for air. So property values, if you look the table A17, this is actually the ideal gas properties of air. So what we have here, we have the U, then and the H and S naught and this V. So you look here, from the property table we can only get these values. So when this question asks that okay, use the property values for the air table, then we can only get these 5 values. So we have got one equations where we got the entropy change, it is equal S2 S1 R P2 P1. So here you can see P2 P1 we know, R gas constant that we know, and this S, this is actually the function of temperature with the absolute zero temperature. So this is some function we defined, we'll discuss it during the lecture. So we'll get simply this value from the table. So S2 naught, it is for final state, S1 naught, it is for initial state. So now this S1 means the initial state. For initial state, temperature is 290. S2 is the final state, the temperature is 330. Let me show you from the table. So for initial state, you can remember the temperature is 290. So this is 290 and it will be the value. So we can say this is actually the S1 naught. And for when the final state temperature is, you see 330. So this is 330. So it will be then S2 naught. So we have S1 naught, S2 naught, this value. So we got these two value. So now what we will do, guys, we will substitute the value here. So let me write it down like this. So we got from the table, it is 1.79783 and S1 is 1.66802 and its unit is kilojoule per kg Kelvin, minus R, this is actually the gas constant, it is constant value, all of you know this. So this is also kilojoule per kg Kelvin. And what else we have? Ln this pressure P2 and P1. So what is pressure P? P2, the final pressure is 600, so 600 kPa, and the P1 is 100 kPa. So if we simplify this, guys, look here, you can cancel out this kPa. So actually our overall unit, it will be like this, kilojoule per kg Kelvin, and it will be negative 0.3844 kilojoule per kg Kelvin. So this is the entropy change. That's actually the solution. It's very straightforward. You do not need to do a lot of calculations. Yeah, so if you know this equation, this expression, then you can easily get it. And S2 S0, I showed you that we calculated this value from the property table. So here you can see it is negative. So I mentioned earlier because here I discussed already why it is negative. So now the second part is, guys, the average specific heats. So that means we need to use the average specific heat. So in this, so we need to use another expression like this, and where we should have the specific heat. So when we discussed the theories, then we already know for constant specific heat problem there is a equation that we can use to calculate the entropy change. So let's solve the second part. Let's say we can say this is B. So we need to use the entropy change of the air during this compression process, and we need to use the specific value. So here the specific heat value, but how we can calculate the specific heat value? So we discussed during when we if you see the theories, when we have this initial temperature, we have the final temperature. Then if we want to use a constant specific heat, in the question it is given average specific heat, so that means you need to take the average temperature. So you can write like this: the average temperature, it is equal 290 Kelvin plus it is 330 Kelvin over 2, because in the question it says, you see, use the average specific heat. So if we want to get average specific heat, then we need to make this temperature average. So it will be 310 Kelvin. So for 310 Kelvin, now we need to use the specific heats, the average specific heats. So when we will get this, look guys, we need to use actually the table A2. You see the table A2, what it is? It is the ideal gas specific heats for common gases. So the first, so this is B. Okay, this is for air. So here we need to use the specific heats, and for ideal gas specific heats, the table is table A2. So we are going to use table A2. You can remember what is the average temperature. It is 310 Kelvin. Look, do we have 310 Kelvin here? We don't have. We have the 300 Kelvin, and the specific heat is 1.005, and we have 350, it is 1.008. So but we know the average temperature is 310, so that means now we need to do some interpolations, right? And you know how to do that. So keep in mind, I will show you. So this value is 1.005, this is 1.008. So now what I will do, guys, I will write down here. So the average temperature, it was 310 Kelvin. So for 300 Kelvin temperature, specific heat is 1.005. For 310, we will calculate it. For 350, it is 1.008. Right. So you know how to do the interpolations. It is pretty straightforward. So this one minus this one. So 310 minus 300, 350 minus 300. Similarly, it is Cp minus 1.005. It is 1.008 minus 1.005. So if we simplify this, the specific heat we will get it is 1.006. It is kilojoule per kg Kelvin. So this is the average specific heat. As we calculated it at average temperature, so it will be the average specific heat. Alright, so now once we know this average specific heat, then we will simply use the formula. So from the book, it is actually the equation number. It is equation number 7.34 for constant specific heat. So you'll see we will use these two formula actually again and again. The first one for properties and the second one when we need the specific heats. So the formula you can see, it is S2 minus S1. That is actually the temperature change. Sorry, the entropy change. You can say delta S. So it is C P average, that means the average specific heat, ln T2 minus T1 minus the R ln P2 minus P1. This is actually the formula, guys. So you do not need to know actually how to get this formula. You do not need to drive it, but if you know this formula, then you can solve any problem. So the specific heat, it is 1.006. I'm not writing the units here. And ln temperature is 330 and it is 290 minus the gas constant is 0.287 into ln the P2 is pressure 600 and the initial pressure is 100. So actually what will happen, it was kPa it is kPa, so we can easily just cancel out this. Anyways, if we simplify this, then it will be negative 0.3842 kilojoule per kg Kelvin, S2 minus S1. This is we got from the average specific heats, but when we used the property tables, then S2 minus S1, it was negative, it was negative 0.3844 kilojoule per kg Kelvin. So it is negligible difference, because the temperature change here 330, this is 290, it is very small, so that's why we're not getting any significant changes. But sometimes we can get significant change, so and then we can use another equation that we will discuss during the lecture. So I believe you understand. Actually, we need to use two different formula. One is this S2 minus S1, it is equal this when you have the specific heats. The other formula is S2 minus S1, this is equal S2 naught S1 naught minus R ln P2 minus P1. So when the question is asking, okay, use the property table, then use this formula. When the question is asking use the specific heat, then use this formula. That's it.